So I would like to start by thanking the organizers for organizing this event and inviting me to speak. It's really an honor for me to be here among all of you. As mentioned, I'll be talking about generative models as queryable world models for today's talk. Reviewing a bit what happened over the past few years, and what we've seen is immense success in training large-scale foundation models. And part of this success has been because of access to large-scale data sets crawled from the internet. However, with the recent advances in generative AI, one question that researchers have started thinking about is whether we can use the generative models as sources of data. And so that's what I'm trying to depict here on the slide. So we have two different models. One that I'm calling a machine learning model 2.0, the other one what I'm calling a model of the world. And so this machine learning model 2.0 can be any downstream machine learning model that you can think of. For example, a recognition model, a foundation model itself, or any representation learning model in general. And this model, as any machine learning model, is data hungry and needs a lot of data to train. However, this particular model has the ability to come up with queries. So you can think of an active learning sort of a scenario, an active acquisition scenario to gather data. And so this model never stops learning, and it uses its own acquired knowledge in order to decide what is useful to improve its own performance. And on the other hand, we have the model of the world, and we can think of this model as a conditional generative model that provides a source of infinite data to train our machine learning model 2.0. And this model can be queried by controlling the generation process in order to get the images that are useful to train the machine learning model 2.0. And so we have this interaction between the machine learning model that we want to train and the model of the world, in that the machine learning model queries the model of the world to gather the data that it needs in order to improve its own performance. And so in light of the recent progress in generative AI, we will cover two different questions in today's talk. The first question is, are state-of-the-art generative models optimized to work as world models? And intuitively, for this to happen, a world model should yield high utility representation. So if we think of the vision space, of the image space, so if we think of text-to-image generative models, for example, this would be yielding high quality or highly realistic images. We would also want this world model to be consistent. So if, again, we think of text-to-image generative models, we would like the images that are generated to be consistent, to represent well what was requested through the user prompt. And we would also like the generations to be diverse. So given a user prompt, we would like the model to be able to get us images that are different from each other. However, if we take a look at state-of-the-art generative models, we see that those are mainly optimized for human preferences. And so this means mainly they are optimized for quality, for image quality, and up to some degree prompt generation consistency. And we have a few examples of that on the slide. So if we take the prompt 2 dogs and a cat, we have 4 different generations depicted on the slide. And although all of the images, or most of them, depict dogs and cats, the exact count is not necessarily reflected in the images. Now, if we move to different prompts, such as a house in Europe, a house in Africa, or a house in South America, what we see here is that we get, again, 4 samples per prompt. And in this case, these samples exhibit relatively low diversity in all cases. The second question that I'll address in this talk is how can we query or how can we control the generative model in order to produce samples that are useful for the machine learning model 2.0 that we want to train. And so let's start with the first question. So the first part of the talk will be on the progress of generative model. And I'll briefly cover a few of the contributions that we had over the past year and a half or so. So the first goal that we set for ourselves was to try to quantify whether there exist geographic disparities in text-to-image generative models. And for that, we introduced the dig-in indicators. The first indicator that we introduced is the region indicator. So this is an indicator that tries to assess both the quality and representation diversity of the generations when a model is prompted to produce images of objects around the world. And so as a proxy for image quality, we use precision that compares the generated images with a reference data set of real images. And as a proxy for diversity, we use coverage, and we would like to know how much of the real reference data set we cover with our generated data. On the slide, we depicted a lot of dots. Those correspond to performances of different models prompted in different ways to get these generations of objects around the world. And what we observed from this first indicator is that some regions tend to exhibit higher realism and higher diversity than others. So notably, when prompting the model to generate objects from Africa, we usually obtain lower realism images with lower diversity as well, especially when compared to the generations that we get when prompting the model for objects in Europe. The second indicator that we introduced is the region object indicator. So this is a zoomed in version of the previous indicator. In this case, we want to see what happens at the object level. And we have some examples of what happens in this slide. So we have 4 columns of images. The first one depicts real images coming from a data set of real images. And those images depict either cars or cooking pots. The same is true for the third column. And then we have the second and the fourth column that depict generations coming from state-of-the-art models when prompted with prompts such as car in Africa, car in Europe, or cooking pot in Africa, cooking pot in Europe. What we observe here is that the generations that we obtain when prompting for objects in Africa tend to be more dissimilar to the ones that we find in the data set of real images. So notably, what we observe, for example, in the case of cars, is that the model tends to generate SUV-like cars that are in relatively rudimentary conditions in very much rural background. And this is not what we find in the real data set of images that were gathered by people located in African countries. Similar observations can be made for cooking pots. And when we prompt the model for object in Europe, so car in Europe, we see that the generations that we get resemble a lot more what we find in the data set of real images, in this case with sedan-like cars in urban environments. The third indicator that we introduced is the object consistency indicator that tries to measure whether the generation process resulted in properly depicting the object that we prompted the model for. And what we observed is that there are models that are more consistent than others, but a lot of them rely more on the region part and in many cases disregard the object that was prompted. So when prompted with, for example, bag in Africa, we see that we get depictions of, again, rural spaces, but the bag doesn't appear anywhere. And so what are the findings of computing these indicators on state-of-the-art models? So what we noticed is that state-of-the-art models exhibit performance disparities in real-world geographic representation. Notably, existing models often have less realism and less diversity of the generations when prompting the models with Africa or West Asia regions than when prompting the models with Europe. Prompting with geographic information, so using the prompt object in region as opposed to only object, comes at a cost of prompt generation consistency, and it also comes at a cost of representation diversity in the generated images. Moreover, models exhibit more region-level disparities for some objects than for others. And of notable concern, what our analysis suggested is that from all the 3 indicators, we observed that progress in image quality has come at the cost of real-world representation diversity. In follow-up work, we analyzed this finding a bit more in depth, and we try to go beyond the geographic diversity. And so we introduced this consistency, diversity, realism Pareto fronts for text-to-image models. So as I mentioned in my first slide of the talk, those are the 3 axes of performance that we care about when thinking of generative models as word models. So we want the model to yield highly realistic images that are sufficiently diverse and that are consistent with their input prompts. Now, what happens, so I'm drawing here 3 plots. Those are the Pareto fronts of consistency of each one of the 2 dimensions here. So consistency versus diversity, realism versus diversity of the generations, and consistency versus realism of the generations. So what we observed from this analysis is that there is actually no best model, and that the model choice when we want to generate images should be determined by the downstream application. what we can see from those plots is that realism and consistency from the last plot both can be improved simultaneously. However, there is a clear trade-off between realism and diversity and realism and consistency and diversity. What about progress in image generation? And I'm depicting here a timeline with some of the latent diffusion models that were open sourced through time. So in both the Digin and the Pareto-Franz analysis, we assessed what happens at the level of image realism, image diversity, and prompt image consistency. And what our findings suggest is that when it comes to image realism, we observe quite a significant progress when comparing the first open source model with one of the most recent ones. However, when it comes to image diversity, we see the opposite. We see that models that were introduced a couple of years ago yield to a higher representation diversity than the ones that were introduced only a few months ago. As for prompt image consistency, we do see progress that is aligned with the image realism, but the progress seems to come a bit slower. So as mentioned, and as reiterated by both of these analyses, progress in image quality at the cost of representation diversity. And so we followed up the work with a user study, with a large-scale annotator study in different regions of the world to understand how annotators in different regions of the world vary in their perceptions of a common evaluation criteria for text-to-image model. And so we collected 65,000 annotations to study how these annotators located in different regions of the world perceive image representativeness, object present, and visual appeal. So let's see what were the findings for image representativeness. So we asked annotators in different regions of the world to answer a few questions such as, could this be a bag in Europe? And we did that for different regions of the world and different objects. What we saw is that for real images, like the bags depicted on the slide, the annotators based in the location that we were asking about tended to think that these were representative of the region more so than annotators that were located outside of the region of interest. And so overall, what happened here is that when the image lacked some marked information or food information or some item that would be believed as representative of the region, then the annotators that were outside of the region of interest thought that the image no longer was representative of the region of interest. However, there was a bit of different behavior when the annotators were shown generated images. So we have on the right side of the slide, the question, could this be a cooking pot in Southeast Asia? And so those images shown there are images coming from a generative model. In this case, annotators that were located in the region that was prompted for thought that these cooking pots are not representative of the region, of their region, whereas the annotators outside of the region of interest thought that this was the case. But in the case of the generated images, we observed mixed results. And when there were some marked items or stereotypes appearing in the image, usually what happened is that annotators outside of the region tended to think that the image belonged to that region more often than the annotators that were actually located in that region. So following up on image representativeness, but now asking the users about the background scene instead of the object itself. So here I'm showing two cases. In both cases, those are generated images, and we're asking the annotators, could Southeast Asia be depicted in the background scene? In the first case, the annotators in Southeast Asia think that this is representative of the kind of backgrounds they would see in their own region, whereas annotators outside of the region think that this is not the case. These answers are flipped for the other case. So again, what we see is when the background is not very informative and essentially could be anywhere in the world, then the annotators of the region tend to think that the background is representative of the region, whereas annotators outside of the region tend to think that this is not the case. Now, if we move to object presence, we also ask different annotators around the world to select the image that shows a particular object. So in the example that I'm showing on the slide, they were asked to select whether the image shows a storefront. So as an example here, all of the images here are generated with the prompt storefront in Southeast Asia. And in this particular case, the annotators in Southeast Asia thought that those were not storefronts, whereas annotators outside of Southeast Asia thought that this could be storefronts. So like what was highlighted here is that the understanding of the perception of certain object changes across different regions of the world. Now, when it comes to visual appeal, so we asked the annotators to mark the appealingness of different images. And here I'm depicting a set of images that were voted as more appealing versus less appealing. And in general, what we observed is that annotators often consider images more appealing, but they also interpret this appeal in contradictory ways, prioritizing in general the background aesthetics of the scene. So if there is a background aesthetic, they would tend to say that the image is appealing, and they prioritize that over the niceness of the object itself. So some of the findings of this annotator study. So we contrast the results of this human annotation study with the common evaluation metrics. I didn't have the time to go into the details here, but for those interested, you can take a look at the paper. And we found that human preference varies notably across geographic locations. Notably, annotators based in different locations often disagree on whether exaggerated or stereotypical depictions of a region are considered geographically representative. When annotating, so we had a few recommendations. The first one is that when annotating for geographic representation, visual appeal, and object consistency, it's good to include annotators that are within the region of interest and outside of the region of interest to capture all of these nuances. Moreover, it's desirable to have multiple annotations per region if we want to capture within region variation. So far, what we've seen is what has been the result of the progress in image generative models. And notably, what we've seen is that we have had an impressive progress in image quality, which is somewhat followed with the prompt generation consistency, although this seems to go a bit behind the image quality, and then followed by image diversity, which instead of improving seems to be the performance in the representation diversity seems to be decreasing across time. And so what I'll be focusing in the next few slides is how can we improve this prompt generation consistency and representation diversity given the current state of the art models that we have. And so what we explored here in order to improve consistency is this improving consistency via prompt optimization. So what do I mean by that? So we start with a user prompt, like the one shown on the slide, which is a raccoon wearing formal attire, wearing formal clothes, wearing a top hat and holding a cane. The raccoon is holding a garbage bag, and this is an oil painting in the style of Vincent van Gogh. And so we started with this prompt, and we feed this prompt to a pre-trained state-of-the-art text-to-image model, and we get some generations. And what we can see here is that these generations partially cover what was requested in the prompt, but some of the elements are missing. For example, we don't see the garbage bag that was requested through the user prompt in this case. So from these generations, what we can do now is feed them to a scoring function. That would be a prompt generation consistency scoring function that would sort of tell us how consistent the generations are with respect to the input prompt. And in this case, I'm depicting the scoring function that is based on a VQA model that tries to answer whether different elements of the prompt were contained in the image. And so now we have a pair of a prompt and a score related to consistency, and we can feed these pairs to a large language model that will try to rewrite the prompt in such a way that the text-to-image model, when prompted with the new prompt, would yield higher consistency images. And we can repeat this process a few times, and this allows us to gather more and more examples to be shown to the large language model as we see that in order to optimize the final prompt. And so after a few rounds of optimization, we end up with a new prompt, which I won't read, but that you have on the slide. And now if we feed this optimized prompt to the same text-to-image model, we get another set of generations. So I'm just depicting two of them in this case. And we see that now more of the elements that were requested through the user prompt do actually appear in the generated images. And so if we feed these new generations to the same scoring function as before, we see that we can improve the results. And so let's see some of the results of this approach. So here I'm going to present results on two data sets, the first one being the MS COCO data set, and we are showing the relative consistency improvement when considering the maximum score across, obtained across the generations at a given step, or when considering the average score obtained at a given step, considering the generations from this step. We're applying this optimization by prompting approach with different combinations of large language model and text-to-image model. And we are comparing this to a simple paraphrasing baseline where we just ask the large language model to rephrase the input prompt without giving it any additional information coming from the scoring function. And what we see here is that as we keep increasing the iterations in all the cases that we do optimization by prompting, and in both when considering the maximum or the average scored at each iteration, we keep improving the prompt generation consistency. We have similar observations when we move to the party prompts data set. So again, we have the same setup, different combinations of large language models and text-to-image models that we couple together in order to do this optimization by prompting, and we compare it to simple paraphrasing baselines. So once again, what we observe is that throughout the iterations, we are able to improve the results when it comes to prompt generation consistency by rewriting the prompts. So let's see these results in the form of a table. So here, what we are presenting is, again, the comparison between paraphrasing and the optimization by prompting approach, which we are calling OPT2I. And we are considering, again, different combinations of large language models and text-to-image models. And in this case, we also consider different scoring functions. So this is what we're calling objective in the table. So here we are considering the DNG scoring function. This is the VQA-based scoring function that I showed a couple of slides back. And then we also consider as objective or a scoring function the decomposed CLIP score. So it's a version of the CLIP score that focuses on the object that must appear in the scene. And we report results again for MS COCO and party prompts datasets, and those are the improvements that we achieve over the baseline, which is using the user-provided prompt as input to the text-to-image model. So now that we've seen that in these cases we are improving in terms of prompt generation consistency, a natural question to ask is, okay, we've improved in terms of prompt generation consistency, but what has happened in terms of image realism or representation diversity? And that's what we try to capture in this second table that appears now on the slide. So we're comparing the initial results. So those are the results coming from prompting the text-image model with the user prompt, followed by the paraphrasing results and the optimization by prompting results. Here we are capturing diversity and quality through the FID score, and we're also disentangling quality and diversity through precision and recall, where precision would be a proxy measure for image quality or image realism, and recall would be a proxy measure for representation diversity. And essentially what these results tell us is that, well, FID remains roughly the same across different approaches, but when we take a look at what happens at precision and recall, what seems to be the case is that we are decreasing precision at the expense of, while we're increasing recall. Okay, so I only have 5 minutes left, so I'll just skip a few slides where we were showing some qualitative results of this process. And just to wrap up on this part of the talk, we introduced the first optimization by prompting framework that improves prompt image consistency. And we showed that this yields notable improvements over the baselines. Qualitatively, what we have seen is that optimizing prompts oftentimes translates into emphasizing initially ignored elements in the generated images, or adding details or changing the world orders. Now, how do we went about improving generation diversity? So this is a recent contribution where we try to leverage what we call a contextualized Venn score. So if we have a generative model and we condition with a prompt and a fixed noise, so we fix the seed, what happens is that we can run the generative process a few times, we'll always get the same image. And what we try to do here is introduce diversity even though we're fixing the seed. So how do we do that? Well, first we start with a memory bank of generated images. So every time we get a generation, we will add it to this memory bank. And then we will use this memory bank to compute the Venn score, and we'll use that as guidance. So intuitively, this contextualized Venn score guidance maximizes the effective number of dissimilar examples. We want to produce samples that are as dissimilar as possible while keeping them close to a small set of exemplar images to ground them to the real data set. And here we have the results that we have obtained. So we see that compared to before, even when fixing the seed, we have induced diversity, representation diversity. So these are some results compared to previous literature. And what we have seen is that by leveraging this contextualized Venn score guidance, so by extending the guidance tools of diffusion models, we can actually increase the representation diversity. Just in the interest of time, I'll skip some of the visualizations, but these are just contrasting what we see with the latent diffusion model out of the box without any guidance compared to the contextualized Venn score guidance. To wrap up on this topic, so we extended the guidance toolbox of diffusion models by driving the generation towards samples that are dissimilar from each other. We showed that this can be effectively done by leveraging the contextualized Venn score. And our qualitative analysis revealed that diversity of the generated images is significantly improved, including along the lines of reductive region portrayals that are present in the original model. I think I don't have time to go over the second part of the talk.
Yeah, there is a little time. Yeah.
2 minutes. Okay, maybe just a high-level overview of that.
But you can get less questions. Maybe like 5 minutes. Yeah, and you can do more 5 minutes, and then we take the questions.
Okay, thank you for that. All right. So we've seen that we had like 3 different axes of performance that we were evaluating when considering text-to-image models as models of the world, or as models that can be queried to gather data to train downstream models. And we saw how we can improve on some of the dimensions that seem to be lagging behind. And so now the question is, okay, provided that we're improving these generative models, how can we query them in order to produce samples that are useful for that downstream machine learning model? And so we go back to the slide that we had in the beginning. So where we have the machine learning model 2.0 that queries the world model, or in our case, the conditional generative model, text-to-image generative model, in order to generate data that to improve the machine learning model's performance. And so the first implementation that we did of that is that for the machine learning model, we considered an image classification model. In this case, we will not only leverage synthetic data, generated data, but also real data. And so we start from this image classification model that is trained on a real-world imbalanced data set. And then we have the model of the world. In this case, we consider a pre-trained state-of-the-art diffusion model. And as the querying mechanism to get samples that are useful for the image classification model, we introduce the concept of feedback guidance. And so we leverage the feedback from a pre-trained classifier to the diffusion model in order to generate samples that are useful to improve the performance of the image classifier. So let's see how we do that. So we start with an imbalanced real-world data set, and we trained an image classification model. Then we leverage feedback signal from this image classification model. Notably, we use as signal the entropy of this classifier in order to guide the diffusion model to produce samples that are high entropy for the pre-trained classifier. And so these high entropy samples are considered to be useful under some definition for the image classifier being trained. So once we get these difficult examples or useful examples for the classifier, we merge them with the real data set that we have before. And so we have this data set that is a combination of synthetic data and real data that we now use to retrain our image classification model. And let's see what are the results of that. So first, what's the effect of leveraging this feedback guidance? So I'm showing first data from the real world data set. This is for jack-o'-lantern, and we see what's the kind of diversity that is contained in the data set. Then we have the LDM generated data. So this would be without the feedback guidance that we have introduced. And so in this case, we see that there is somewhat little diversity in the sense that the background of all of the generations is most of the time grayish, and there is most of the time a single pumpkin that is depicted, and there's little variety in the colors. However, when we leverage the feedback guidance, and so those are generations of images that induce high entropy in our classification model, we see a lot more diversity in the number of objects that appear in the scene, in the backgrounds, and also in the colors of those objects. So what do the results look like? So those are results on the ImageNet long tail, evaluating overall performance across all the classes, but also zooming into the classes for which we have many examples, medium number of examples, and few examples. And we're comparing to approaches that do leverage synthetic content coming from an image generative model, and approaches that do not leverage synthetic content from a generative model, but instead may leverage other forms of synthetic data, such as applying data augmentation to the real data. And what we see is that across the board, we are yielding improvements over prior art. We also analyzed how adding synthetic samples may saturate the performance. And so that's what's depicted here on the accuracy for the class few. What we see here is that generating up to 1 million examples keeps improving the performance, whereas after that, it becomes difficult to leverage the synthetic samples. Some hypothesis behind that is that is related to what we have discussed in earlier parts of the talk about the representation diversity that can be achieved through these generations. I'll skip the additional results on the Nico++ and Places LT dataset, and I will wrap up this part of the talk. So what we have seen is that by leveraging the feedback guidance, we are able to boost the performance of our original classifier. And this results in improvements of up to 4% on the represented classes in the ImageNet dataset. We have similar observations for Nico++ dataset and for the Places LT dataset. Hopefully, our framework paves the road towards effectively leveraging these high-performance text-to-image models as data sources that can be queried for downstream applications. Just wrapping up the presentation now, we started with the first question, which was, are state-of-the-art generative models optimized to work as world models? And what we have seen is that through different studies, we have tried to quantify the progress in text-to-image models, and we've seen that this progress has been mainly driven by the image quality improvements or the image realism. The progress in image quality or realism has, however, come at the cost of representation diversity. We've seen that we can improve upon consistency and diversity by leveraging different methodologies, notably by leveraging optimization by prompting, so leveraging LLMs, or by extending the guidance toolbox of diffusion models with the contextualized and-score guidance. We also asked the second question, which was, okay, provided that we have a sufficiently good model of the world, how can we query or control the generative process in order to produce examples that are useful to train the downstream machine learning model? And in this case, we have seen that leveraging feedback guidance from a pre-trained image classification model, in our case, was effective in order to drive the generation process to produce samples that were useful for the classifier, and this resulted in improvements downstream. However, I didn't cover this today, but we tried different criteria, and the results that I presented today were for maximizing the entropy of the classifier as criteria. However, different criteria yielded notably different results, and I think there is an open question on how to better leverage this or how to better design feedback guidance strategies in order to help us get there. I wrap up. I would like to thank all of my collaborators with whom it wouldn't have been possible to perform all of this work. And I'll close the presentation. Thank you all.
I do have a question. Like mainly when you were mentioning like kind of like that relation, kind of like trade-off, like precision of recall, where you want to maximize the kind of recall from diversity and productivity, precision, kind of business similarity. What is that real trade-off? And like there is kind of like diminishing between at some point that you need to get this how much diversity recall I can get for this precision. You know, like kind of elaborated on that.
Yeah, I can provide maybe a bit more details on this analysis. So, well, first of all, these are like proxy metrics, right, to measure sort of image realism and image diversity. When I say proxy metrics, it's because both in the case of precision and recall, we are relying on a reference data set of real images. And so this means that we are constraining the definition of what is high quality or what is high diversity to these real data sets. And so I think this is maybe like an important point maybe to answer your question, because, well, what we have seen is that, well, first, it's very important to understand what is the data set that you're selecting. So if we go ahead and just pick any data set as reference data sets, probably this data set by construction will not have the representation diversity that we want to quantify against, right? And so although you can think of diversity in a slightly different way in this case, and we have seen that in the Pareto-France paper, so that you can still see this, observe this trade-off. Maybe the definition of it is a bit different. However, if you do leverage data sets that have been constructed explicitly to capture this representation diversity, then I think this trade-off becomes more and more evident. Now, maybe the question that you're hinting is like, well, it seems to be a trade-off. So so is it really a trade-off, or is it just like the results of what we have seen so far? And so this is, I guess, an open question. And what we're trying to do in our research is to move away from this trade-off and try to push the research towards models that can be at the same time, that can yield at the same time high quality images and that are diverse and representative of the world.
That is all the time, this of the text-to-image models are improving. So all this is valid now for the current state of that. But what is your feeling in the future that is when these models are improving, so will this be so big difference?
Yeah, so those are like good questions. So the first one was more about like grounding these concepts into like the metrics, like the performance axis into the metrics that we're using. So I do agree with the statement that those are like sort of semantic concepts. And of course, the measurements that we're using here or the metrics that we're using are only like proxy metrics. What we have been doing like to sort of capture this idea, this semantic idea, is that all of these metrics are computed in the feature space of considering an entire image. And so, for example, for consistency, you can think of consistency, again, it's going to be an imperfect metric, but the way that you can think about it is, okay, you have a generated image, you have the text prompt associated with these generated images. Now I can embed both the image and the text prompt by leveraging a pre-trained vision language model that is trained to sort of push together these two representations, right? And now, like, what's the distance of these two representations in the feature in the feature space? So that's one way of sort of capturing the semantics of consistency. Of course, this will be sort of at high level. Probably you will lose some nuances at the details of the image, but now it depends also like how detailed the text prompt is, just to give you an example. And the same applies to precision and recall. So the way we compute this in practice is by constructing or estimating the manifold of real images. And this manifold estimation of real images relies on the extraction of features of these real images that we're using as reference. And then sort of computing how close the generations that we have are in the feature space to those real images that we used as a reference. So just to briefly address the first question. For the second question, you were thinking like what's sort of moving forward, whether this gap will be exacerbated or not. So I do hope that through research, we will be able to work on mitigations that go beyond what we have been doing so far. So far what we have done is take these pre-trained models and then do interventions on them at inference time. And we can keep doing that, but I think there is a limit to this kind of approaches if we want to increase representation diversity, also for the simple reason that if you have the code like that to do this guidance, you can very easily sort of comment the line that is trying to improve upon whatever aspect of performance you care about, in this case, representation diversity, and then it's all for nothing, right? And so moving forward, what I'm particularly interested in is how do we think of embedding these concepts of diversity or this concept of responsibility, more broadly speaking, in the weights of our model. So this means like considering the whole pipeline, from the data to the training to the inference time interventions. And what I would like to see in the next maybe 2 or 3 years is progress in this direction, so that we are not in the situation that we keep growing the gap that we're observing between the progress in representation diversity and the progress in image quality.
One question I cannot stop from asking, maybe it's not like a popular question, is like, when you show these examples of East Asia or South Asia, I mean, we as Latins, so I just try to like look back to these questions when you see like American movies, like, I don't know, like Bogota or any other country in Latin America. It seems like all movies usually show like Django or something like that. And it's like, that's not Bogota. I mean, just talking about Colombia. So same thing applies in here. So I don't know if you also analyze like this sort of bias. I mean, like, yeah, it seems to be like when you talk about like thoughts of these of different countries, so it seems to be like looking trashy, if I would say, and you're like super shiny and clean.
Yeah.
So I guess it's like a sensitive and diversity question. So
yeah, no, I think that's a great question, and it's definitely sort of the underlying question that we're trying to address, right? So I think to answer this, maybe like, okay, in the first work that introduced the indicators and that tried to quantify that, the way we implicitly captured that, although it was not like pinpointing it in the way that you're mentioning here, is by leveraging these sort of reference data sets that were collected in region. And so that would capture the true representation diversity of each location. So that was more on the automatic side. But I think like the work where we tried to address the question that you mentioned is through the annotation study. And so in the case, what we did in the annotation study is present images that were like real images taken by people located in particular regions of the world, and show them to the annotators so that they could answer whether this image was representative of that region. And we did that for real images, but also for images that were generated by text-to-image models. And so we prompted these questions to annotators that were inside the region where the images were taken, or where the prompt that we used to generate the image contained this region information. But we also showed these images to annotators that were outside of the region. And I think that's what the results that we got are contrasting exactly what you're saying. So for real images that usually are, according to annotators based on the region, are representative of the region, are not perceived like that by annotators that are outside of the region. And for the generations, it's a bit more mixed. So it depends now on how the generation looks like. But for more stereotyped, let's say, generations, usually what happens is that annotators that are outside of the region tend to think that this looks more like the region than annotators that are within the region. So I think this is just highlighting the problem that you just mentioned. It's not a solution, and like what we're hoping to address moving forward is again like how can we mitigate that?